All right, another chance to do some Calc 1 problems. Here we're doing some of the very advanced stuff with differentiation and starting to get into integration. Woohoo! Nice! And so lots of stuff to look forward to. We got 7 fun problems ahead of us. But as always, we start by putting our name on here, because if we don't put our name, we won't get the credit. All right, well, let's begin. Number 1, we want to use Newton's method to find an approximate solution of x cubed plus 3x equals minus 1. And it says start with x0 equals 0 and find x2. Now let's just quickly remind ourselves what Newton's method says. Now Newton's method is about roots. So we have to find the roots. And so in other words, you imagine that we have a function and does something like this. We want to find that. In other words, where the function crosses the axis. Well, we want to find it. We don't know how to find it. So I say, okay, I make a guess. Here's a guess. All right, well, we're not right. Newton's method says, hey, look, we're not getting it right. We're about getting it better and better answers. So the way we do is say, okay, well, let's come up to where we currently are with our guess and say, use the tangent line, which will follow the function along, and that'll get you a lot closer. And so in other words, better and better, right? So it's an iterative idea. You try a guess, get a better guess. Now take that guess, get a better guess, and pretty quickly, in many cases, we've got a really good guess. Not exact, but really good. For engineers, it's good enough for all intents and purposes. So what you do, and here's the rule, is it says, well, if you just sort of say this is our current guess, which we say x sub n, and here's our next guess, which is xn plus 1, you follow the procedure that says our next guess is our current guess, and then there's a correction term. And that is based upon the value of the function and how steep the tangent line is. So of course, if our function is very close to 0, we don't need to change much. If our tangent line is very shallow, we change a lot. If it's very steep, we don't change much. And so it works out to be minus the value of the function over the derivative of the function. Okay, so that's the procedure. How do we apply it here? Because it doesn't say find a root, and it says find where x cubed plus 3x equals minus 1. See, this would be where it equals 0. But that's okay. What we do is we move things around. So we say, well, this is the same as saying we want x cubed plus 3x plus 1 equals 0. See, we can add 1 to both sides. And so this part, that's our f of x. That's what we're trying to find our root for. Well, we make a few more notes here. F prime of x, well, that would be 3x squared plus 3. And we now say the following. We have that x n plus 1 will be x sub n minus, on the top, we plug it into the function, x sub n cubed plus 3x sub n plus 1. And downstairs, plug in the derivative, 3xn squared plus 3. Okay, so we begin. Initial guess, they told us, start with 0. All right, x0 is 0. What is x1? So if we just follow it in here blindly, we say it's x0 minus x0 cubed plus 3x0 plus 1 over 3x0 squared plus 3. Now the nice thing is everywhere we see x0 is a 0, so almost everything goes away except the minus 1/3. So now we have a new guess, minus 1/3. Okay, well, but let's get a better guess, because that's x1. So what is x2? Well, that's x1 minus x1 cubed plus 3x1 plus 1 divided by 3x1 squared plus 3. Right? Because it's just plugging in n equals 1 everywhere we see here. And now, well, our guess. So it's our current guess, negative 1/3 minus negative 1/3 cubed plus 3 times negative 1/3 plus 1 over 3 times negative 1/3 squared plus 3. At least a little bit is pretty quick. Negative 1/3 times 3 is negative 1 plus 1, 0. That's not so bad. Well, okay. Let's see. Probably want to clean this up a little bit. So you have negative 1/3 minus, now upstairs, negative 1/3 cubed would be negative 1 over 27. Downstairs, negative 1/3 squared would be a 1/9 times 3 would be 1/3 plus 3. Well, okay, multiply top and bottom by 27. And if we do that, we'll get negative 1/3 minus a minus 1, so actually we can make it a plus 1, over 1/3 times 27 is 9. And then we have 3 times 27, and that's 81. And so we take 9 plus 81, we get 90. All right, so negative 1/3 plus 90. All right, well, now what do we do? Well, the next thing for us to do is we combine, right? So we want common denominator would be 90. So this would be negative 30 over 90 plus 1 over 90, which gives us our final answer of negative 29 over 90. Good, good. And so now that's not to say that's the root, remember, but that's an approximation. And usually not a bad one, not a bad one. All right, well, good. We're off to a good start. One problem down, many more still to come. Number 2, we want to find an estimate for an integral. The integral from negative 1 to 8 of 4x f of x plus 1 dx using a Riemann sum with 3 equally sized intervals, using the midpoint of each interval, and using the information in the following table. And then we have a whole bunch of stuff. Now they gave us a lot of information. Are we going to need it? Not all of it. In some sense, we're being tested on which pieces of information do we need. Now, when we think about Riemann sums, you should think of this as like, oh, it's a bunch of rectangles. That's what's going on here. So the idea of a Riemann sum is saying, well, let's just imagine that we are trying to find an area of something, and we're going to say, oh, it's hard to find the exact thing, so I'll treat it like as though it were a series of rectangles. Now, how does it work? Let's go into our case. So we're going from negative 1 all the way up to positive 8. And we're told 3 equal intervals. Okay, so from negative 1 to positive 8, that's distance 9. So if we take distance 9 and chop it into 3 parts, that would be length 3 for each part. So negative 1 add 3 would give 2, 2 add 3 would give 5, 5 add 3 give 8. And so we want to have a rectangle over each piece. Now, where do we figure out the height? Well, that's where another piece of information comes in, because we can say, look, pick a number in between negative 1 and 2 and use that to figure out the height. And similar for 2 to 5 and for 5 to 8. So we have to say which point. And they told us the midpoint. So what's halfway between negative 1 and 2? Well, halfway is their average. If you add these together, divide by 2, you get 0.5, right? Negative 1 plus 2 is 1, divided by 2 is 0.5. And now you can just say, okay, do the same thing, or just shift by 3, and lo and behold, we have all of our endpoints. So 0.5, 3.5, and 6.5. Okay, so we're going to use these and plug them in and find our various heights. Now, we'll go through and actually do this in a second. And the idea is once we find the area of these rectangles, life is good. That's our approximation. So, let's start with our first rectangle. Well, what's the area? Well, we have the width at the bottom. So that would be 3 times the height. Now to get the height, we're going to plug in 0.5, not into the function, but into what we're working with. So we plug it into here. So the height would be 4 times 0.5 f of 1.5. Okay, so that's the area of this first rectangle. Second rectangle, the width, still 3. So they all have width 3. So, okay, so we also have 3. Plug in 3.5. So we have 4 times 3.5. And then we're going to have f of 3.5 plus 1 would be 4.5. Now the last rectangle. 3, that's our width. Our height, we plug in 6.5, so we have 4 times 6.5, and times f of 6.5 plus 1, 7.5. All right, so those are our 3 areas. That's our Riemann sum. So we just have to figure out what are these values. So looking at our table, what do we need to use? Well, we need the f of 1.5, the f of 4.5, and the f of 7.5. And so we start plugging in these numbers. And okay, some of them are easier to use than others, but so at 1.5, we have 2.5. So we have 3 times 4 times 0.5 times 2.5. Here, 4.5, we have 0. So we have 3 times 4 times 3.5 times 0. And finally, we're going to have 3 times 4 times 6.5 times 0.5. Now, one of these is pretty quick. 0 is hard to recover from. All right, for the other ones, let's work this out. 3 times 4, 0.5, I'm going to write this as a half. 2.5, I'll write that as 5 halves. And then the other term, of course, we'll write the 0 just because I was there. 3 times 4, 6.5, well, that's really 13 halves. And 0.5 is 1 half. So the 4 and the 2's cancel, 4's and the 2's cancel again. We have 3 times 5, which is 15, plus 0, plus 39. And if you add 15 plus 0 plus 39, you will end up with 54. And we're done. That's it. So we took our shape. We didn't know what it was, but we didn't have to. We said, look, let's break things up. Everything's a rectangle because we're after an estimate, not the value, an estimate. And then we were able to say, okay, we knew the widths of the rectangles. We used the midpoints to get the heights of the rectangles, being careful to use not this table, but to use the function that we're integrating, which of course later refers back to the table, but make sure this is where it's easy to trip up. Okay, and then we just worked out, added everything up. Life is good. Life is wonderful. 2 problems down. We're feeling good. And hey, we got this test. We're going to do great. Number 3, solve each of the following parts. You do not need to simplify. Okay, so we start with part A. We're after the derivative from pi up to x squared of cosine t cubed dt. Now, the good news is you might say, hopeless. How do you integrate cosine t cubed? And the answer is, you don't. You can't. But do you have to? Well, you don't, because there's this lovely fact that says the derivative of the integral from a to x of f of t dt is f of x. So, all right, oh, great. Well, the only thing is it's not x, it's x squared, but no worries, it's chain rule. So this would be cosine of the inside piece is that function. So that's x squared cubed. And now times the derivative of x squared, which is 2x. So that would end up being 2x cosine x to the 6. Because if I take x squared cubed, you multiply. All right, find the integral from -1 to 3, 2x squared plus 3 dx. All right, well, this we can do by saying find an antiderivative. So, for example, the antiderivative of 2x squared, we could choose it to be 2/3 x cubed. The antiderivative of 3 is 3x. And now evaluate from -1 to +3. Well, you plug in +3, and you get 3 cubed, 27, times 2/3, that's 18. 3 times 3 is 9. Subtract, plug in -1. 2/3 times -1 cubed, well, that's a -2/3. And 3 times -1 will be a -3. Well, okay, 18 plus 9 is 27. And then we're going to add 3. So this is 30 plus 2/3. Well, we can make that 90/3 plus 2/3 could make this 92/3. And there we go. All right. Well, that's not so bad. Well, now, this next one. F of x is sine of x times x cosine squared of x, and evaluate the integral from 0 to pi halves f prime of x. Whoa, oh my gosh. Oh, this looks terrible. But think about what we just did. This one said, oh, find an antiderivative, evaluate at the endpoints. Well, what's the easiest antiderivative of a derivative? The function. So this is the same as just f of x, but we have to evaluate from 0 to pi halves. Well, for that, what do? We plug in. We say, okay, when you plug in pi halves, you get sine of pi halves to the cosine squared of pi halves, and then subtract sine of 0. Oh, wait a second, sine of 0 is 0, and okay, so that's just 0. Now, sine of pi halves is 1, so this is 1. Pi halves to the cosine squared of pi halves. Now, cosine of pi halves is 0. Pi halves to 0 is 1. So you get 1. That's the whole answer. And then there's part D, and there's not a lot of space left, but it says, what important theorem is required to solve parts A to C? Hint, it's rather fundamental. I think they were trying to be a little bit punny. All right, well, come on, they gave it away here, right? What are we doing? Fundamental calculus, it can mean one thing. It's the fundamental theorem. And you know what they say, you can't spell fundamental without fun. So, Yeah, it's the fun part of calculus. It's really the part of calculus that says, oh, this thing called integration and this thing called differentiation, they're connected. So, all right. Well, that was pretty good. Good progress. Wonderful. Let's keep moving on. Number 4. Find each of the following. So let's start with part A. We have this integral of sine x minus 1 over x squared plus 3 over x. Now the nice thing is integration is linear, which is just a fancy way of saying when you have addition and subtraction, you can break them up into the little pieces. So in other words, instead of thinking this as one big integral, we'll think of it as 3 smaller integrals. And we want to do that because that makes each one a little bit more bite-sized, easier to work with. So we have sine of x dx minus the integral 1 over x squared plus 1 dx, and then plus 3 integral 1 over x dx. Okay, now each one of these are things we recognize. In other words, we've gotten so used to taking derivatives, we say, oh, I know a function whose derivative looks like sine, so going backwards, I can find the antiderivative of sine. In particular, sine is, got to be careful here. The derivative of sine is cosine. Okay, derivative of cosine is negative sine. So the antiderivative of sine, you have negative cosine. So negative cosine x. The integral of 1 over x squared plus 1, near and dear to my heart, arctangent. So minus arctangent of x. 1 over x, another one, that's very popular. Don't forget the 3, natural log x. And notice we could pull the 3 out because we are allowed to pull out constants. Are we done? Plus c. Because when we write an integral sign like this without bounds, what we're really saying is, give me an antiderivative. And what we should do is we should say, there's a whole family of antiderivatives. They all differ by a constant. So we should have a plus c. Now, I would be remiss not to make a comment here. If you want to be super careful, you can put absolute values there. I'm kind of a little bit okay with not doing that, but I know some people are very particular about that. There's reasons to put them there, there's reasons not to put them there, and there's a very long discussion to be had. So when in doubt at this level, put them there for now. Come back in a few semesters when things have gone a little bit more complex, we can talk again. But all right, that's part A. All right, done. Part B. This one looks more interesting. We have the integral from the cubed root of 5 to the cubed root of 41 of x squared divided by the square root of 2x cubed minus 1 dx. And you might say, well, I don't know a function whose derivative is that right away. So, okay, well, that's not the end. One of the big things about math, and in particular about our calculus class right now, is we're learning how to rewrite. And most math problems are solved by first rewriting them to something more palatable. Now, in our case, what's more palatable? Well, we can use the idea of substitution. It's our biggest tool for rewriting integrals. Well, I should say algebra, of course, is our big tool, but after algebra, substitution. And when we're looking for substitution, we like to say that substitution is an inside job. So we're looking for a function inside of some other function. With that mindset, it's easy to spot a good candidate for substitution, namely this 2x cubed minus 1. That's on the inside. So let's try that. Now, it may or may not work. I strongly suspect it will. But there's a beautiful idea in math, which is you try something. If it doesn't work, you try something else. Sometimes you get it right the first time. Sometimes you might need to do a second time. No worries. We're patient. So we'd have du would be taking the derivative, 6x squared dx. And aha, we have an x squared dx. Good substitution has been made. We don't have a 6, but that's okay. We can rewrite this as 1/6 du is equal to x squared dx. It's one of the nice things about being linear is it's simple to move constants around. So if you're off by a constant, good enough. You have what you need. So let's see what we have. So we currently have the integral x squared dx becomes 1/6 du. The square root of 2x cubed minus 1 over there becomes 1 over square root of u. And now the bounds. Let's be careful here. We oftentimes don't write this, but we have to remember that these are not just arbitrary numbers. These are tied to our variable. So when we talk about cube root of 5, x equals cube root of 5. Cube root of 41, x equals cube root of 41. So now when we come here, what do we want? Well, we want to get u bounds because we would want to go forward. When we're doing substitution of a definite integral, always forward, never back. So we got to update our bounds along the way. So the way we do it is we use the relationship. So we say, okay, plug in cube root of 5. Cube root of 5 cubed is 5, times 2 is 10, minus 1 is 9. So lower bound is 9. Okay, up here, cube root of 41. Then make that cubed is 41. And then you double 41, you get 82. You subtract 1, you get 81. Okay, so we're going from 9 to 81. Okay, so there's one other thing. We can pull the 1/6 out, integral 9 to 81. This current notation is not calculus friendly. Calculus friendly says I want to express it the way the rules are written. So I want to rewrite it as u to a power, and the right power would be to the minus a half. Half since there's a square root, minus because it was in the denominator. Now we're ready. So the rule says add 1 to the exponent. Negative a half plus 1 would be a half. So we have 1/6 u to the half. And then you have to divide by the exponent or multiply by the reciprocal. So the reciprocal of a half is 2. Evaluate from 9 to 81. No c here, it's a definite integral. C here for indefinite integral. All right, well, we're almost there. A 6 times 2 would be a third. 81 to the 1/2, that's the square root of 81. That's 9, minus 9 to the half. 9 to the half is 3. 9 minus 3, 6. 6 times a third is 2. And a nice answer. And a nice answer. What a crazy way to express 2, but that's all right. We worked it out. We were patient. Good. And now we're halfway done. We're over halfway done. Woohoo! Let's go ahead and finish that other half. Number 5. Find a value of c that makes the function. So we have this f of x, which is 9 minus 9 cosine 3x over 15x squared if we're not 0. And then c if we are 0. Continuous at x equals 0. So what's going on? Well, continuity, remember what is that? It says no surprises. So if I'm continuous at 0, I need to have that the limit as x goes to 0 of f of x should equal f of 0. Now we know what f of 0 is. It's c. So we say, oh, okay, so this should be equal to c. And here, what if we're approaching 0? Well, if we're approaching 0, we're using this expression here. So we say, oh, so this would be the limit as x goes to 0 of 9 minus 9 cosine of 3x over 15x squared. So it says, oh, this question is really asking us for this limit. All right, so we're after a limit. And at this part of the course, we're like, I know, it is le hôpital, right? Mon ami, yes, we are absolutely going to be doing le hôpital. So let's go through and be careful, because of course we want to make sure we get all our points. Well, we also want to make sure we understand. They go together, right? The more you understand, the more points you get. So you say, well, what happens if you plug in 0? So for every limit, that's the first thing you do is like, well, plug it in. What happens? Well, downstairs you get 15 times 0. Okay, that's a 0 downstairs. Upstairs, cosine of 0 is 1. So you end up with 9 minus 9, which is 0. And now that's not our answer. It's not 1. 0 over 0 is not 1. 0 over 0 means more work. More work. And our work is le hôpital. Mon chéri, le hôpital. Okay, so le hôpital says, since it goes to 0 over 0, you can now think about what happens here when you take the derivative of the top and the derivative of the bottom. So the derivative of the bottom is the easier one, so that's where I start. Derivative of the top, derivative of 9 is 0. Derivative of cosine, well, it's positive. Well, derivative of cosine is negative sign, but there's already a negative there, so it's going to end up with a positive. We have to bring a 3 out. There's already a 27 there. Sorry, we have to bring a 3 out. There's already a 9 there, meaning we have a 27. Okay, so 27 sine of 3x. And now, again, what's happening at 0? Well, we plug in. We get 0 downstairs still. All right. What do we get upstairs? Well, we have sine of 0 is 0. Okay, another 0 over 0, which means even more work. That's right. You can do it more than once. Le hôpital, you keep going until you either realize it's not going to work or you get an answer. All right. So take derivatives. Downstairs is 30. And at this point we can say, game over, man. Game over. Why? Because that's not 0. We're not going to get a 0 over 0. So whatever happens, it's going to happen right now. All right. Derivative of sine is cosine. But when we take the derivative here, we have to take derivative of the inside as well. So there's going to be a 3 come out again. So 27 times 3 makes 81. Cosine of 3x. And, well, as we said, it doesn't go to 0 over 0. So plug it in. And what do we get? Upstairs, we get 81. Downstairs, we get 30. Well, we can simplify it. Both of those are divisible by 3. So that would be 27 upstairs and 10 downstairs. 27 tenths. And there we go. So that should be the value for C, 27 over 10. And if you're an engineer, you could say, aha, this is 2.7, and then add a few digits for precision. Right? Isn't that how engineers work? I don't know. It seems like they like 4 digits. But anyways, 27 over 10. Nice answer. Good. Done. 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 Number 6. The function f of x is x plus the square root of x minus 2 on the closed interval from 3 to 11 satisfies the conditions of the mean value theorem. All that means to say satisfies the conditions is it's continuous and differentiable. All right. Find the value of c satisfying the conclusion of the mean value theorem. And at that point we're like, maybe we should remind ourselves what the mean value theorem says? Good idea. Let's do that. Now you might say, mean. Yeah, that sounds right. Are mean instructors? No, not that kind of mean. Mean here means average. So it's an average value theorem. So there's nothing cruel about this problem. And in particular, it says, well, we can talk about the average rate of change between 3 and 11. So that would be take the value of the function at 11, subtract the value of the function at 3. over 11 subtract 3. So this is your average rate of change. And the mean value theorem says, hey, this is equal to the instantaneous rate of change at some point. So in other words, if you know your average speed on a trip, then at some point on that trip, you had to be going exactly that speed. So oftentimes you're going under, oftentimes you're going over, but at some point you were just right. Okay, so that's the c we're after. So the way we're going to do it is we have to take the derivative and plug in c, and in the meantime we have to figure out what this number is. So let's do these pieces here. So we'll start with the derivative. Our function f of x is x plus the square root x minus 2. If you like, that's x plus x minus 2 to the 1/2. So f prime of x, well, the derivative of x is 1. And we write it with this notation to make it more calculus friendly. It fits the rules better. So the 1/2 comes down, x minus 2 to the 1/2 minus 1 is minus 1/2. Here to the inside is 1, and so we're good to go. So this is also 1 plus 1 over 2 square root x minus 2. Okay, so that's going to help us find that. All right, well, let's go and figure this out here. So we have f of 11 minus f of 3 over 11 minus 3. Now, plug in 11. We're going to get 11 and the square root of 11 minus 2. 11 minus 2 is 9. Square root of 9 is 3. So that would be 14. That's what we get when we plug in 11. Plug in 3. 3 plus 3 minus 2. 3 minus 2 is 1. Square root of 1 is 1. So we have 3 plus 1, which is 1. So 14, 3 plus 1 is 4. 14 minus 4 over 11 minus 3. Okay, so that would be 10 over 8. Okay, 10/8. So here we go. We're going to put things equal to each other. So 10 over 8 has to be equal to 1 plus 1 over 2 square root of x minus 2. Subtract 1 from both sides. And, oh, by the way, we could have pointed out that 10 over 8 is the same as 5 over 4. Subtract 1 from both sides. And that tells us that 1 over 4 has to equal 1 over 2 square root of x minus 2. Let's flip both sides. That tells us 2 square root of x minus 2 has to equal 4. Divide by 2. Square root of x minus 2 has to equal 2. Square both sides. X minus 2 has to equal 4. And finally, add, and we get x equals 6. So that's what we're after. Now, I said x. In retrospect, I should not have been saying x. I should have been saying, of course, c. Well, that's an easy fix to make. So we just come through here and just say, aha, c. c equals 6. Now, there is one small technicality that we should address, which is when we get to this point, we may have found multiple values for c. We didn't in this case, but other times we might. Which value for c do we take? Well, the answer is we take any value for c, and we might have several, as long as it's between 3 and 11. So one of the things about the mean value theorem is that it has to be between 3 and 11. So we should check 6 is between 3 and 11, so that's a good thing. If our answer had been 15, we were guaranteed that we made a mistake. And of course, if we're guaranteed we made a mistake, that means we have a chance to go back and fix ourselves. So it's one thing to sort of keep an eye out for. Make sure the value you find for anything satisfying the mean value theorem is in between your endpoints. Okay, well that's that problem. Just one more to go. All right, let's finish it up. Our final problem, number 7. Find the function y that solves the separable differential equation dy dx is negative y squared secant of x tangent of x, and satisfies y of 0 is equal to 1. All right, now we know it's a separable differential equation because it tells us. And for this, we know there's a nice procedure, and it's 3 steps. You separate, you integrate, right? Even flows, right? Separate, integrate, and the last step I call uncomplicate. Now, that seems overly complicated for a word, but basically means solve for y, solve for c. So we go through and do our steps. So we'll start with the separation step. So now we're doing separation. All right, how do we start? Well, we're going to think of this dy dx as 2 pieces, dy upstairs, dx downstairs. And we're going to put all the y's on one side, all the x's on the other. There's not too much we have to move around. Well, we can move this part across, and of course we can move this part across. So if we do that, well, we do this by dividing or multiplying. So this would become minus y minus 2 dy is equal to secant of x tangent of x dx. Okay, so that step is done. And I did not give myself enough room. Typical Steve. Okay, what happens next? Well, now that we've separated, and it's easy to check if you separate, just say, is it all one type of variable? Yes. Is it all one type of variable? Yes. Okay, then you're separated. Now you're integrating. So you integrate. Minus y to the minus 2. Well, we're set up, right? So this becomes y, you add 1, so it becomes minus 1, and then you divide by minus 1. There's already a minus in front. Minus over minus makes 1. So y to the minus 1, which, by the way, is another way to say 1 over y is equal to integral of secant x tangent x. Well, what's the antiderivative of secant tangent? It's secant. So that's nice. Cool. And of course, plus c. Now we come to uncomplicate. And that means is we need to solve for y and solve for our constant. Now, we can solve for our constant at any point that's convenient. So we'd say, is it convenient? Well, let's check. If you plug in x equals 0 and y equals 1, you'd have 1 equals secant of 0 plus c. Do we know what secant of 0 is? Actually, we do. So secant is 1 over cosine. Cosine of 0 is 1. So secant of 0 is 1. 1 equals 1 plus c. So that says, oh, c is 0, right? The 1's cancel. And, we're almost there. So we now know that 1 over y equals secant of x. We flip both sides because we want to solve for y, right? Find y. So we get that y is flipping secant. Well, we just mentioned secant is 1 over cosine. So flipping secant, we get back cosine. And we're done. That's it. That's the problem. We made it. We did it. Woohoo! Nice. All right. Well, I hope you're ready. And if not, there's still time to practice. You can do it. I believe in you. Pass this class and go on to bigger and better things. So I hope I can get to see you again. All right. Bye.